Hey friends, this is Vidhan. Welcome you to my channel. First of all, I want to thank all you who have subscribed to my channel. I also want to thank all who have liked and commented on my videos. This is really amazing. This is really motivating for me and I'm really grateful for this. And I shall be doing my best to get you helpful videos on CSI Net Physics solutions. If you have any suggestion regarding my videos, then you are most welcome. You can comment anytime. This video is about finding eigenvalues of antisymmetric matrix from June 2012 part C. Part C question has 5 marks for each question. It says the eigenvalues of antisymmetric matrix A where n1, n2 and n3 are components of a unit vector. This very condition that n1, n2, n3 are components of a unit vector is something which is to be used later in our problem, but not in the beginning. But it has a use, we will see. So we will approach this problem in 3 sections. First of all, we will discuss about antisymmetric matrix. Secondly, we will discuss about eigenvalues of antisymmetric matrix. And in the end, we will find the eigenvalues of this matrix using our standard methods we know, characteristic equation or by using characteristic polynomial equation. So first of all, antisymmetric matrix. So we have written down our this is our given matrix. I have already written down. For a matrix to be antisymmetric, there are 3 conditions. What are those conditions? Number 1 condition, the matrix must be square matrix. Second condition, the diagonal elements must be 0. And the third condition is doing the transpose on the matrix, we should get negative of the matrix. So if we see, yes, this is square matrix. This is of order 3 by 3. We can say this is odd square matrix. Why odd? Because its order is 3 by 3 and 3 is odd. If this was a square matrix of order 2 by 2, then it would have been even matrix. And if it is 5 by 5, then odd. If it is 4 by 4, then even, etc. And yes, the diagonal elements are 0. And A transpose should be equal to minus A. So let us check that if we do the transpose over this, then rows will be columns, columns will be rows, we know. So the first row will be the first column, 0, minus n3, n2. Second row will be second column, n3, 0, minus n1. And the third row will be third column, minus n2, n1 and 0. If we take a minus sign and take this out as common from all the elements, then we have 0, this is minus n3, this is plus n2, this is plus n3, this is 0, this is minus n1, this is minus n2, this is plus n1 and this is 0. Now compare this with this. They are same things. That means it is A, minus of A. And what was this? Transpose of A. So really, this matrix satisfies all the conditions. So this is an antisymmetric matrix. But we don't have to check like this because it has already been said in our problem that it is an antisymmetric matrix. But we have looked at this for knowledge sake. Now, 2 properties I'll tell you of an antisymmetric matrix. Not the conditions but 2 properties. One is the determinant of antisymmetric matrix is always 0. You can find this as an exercise and you will find it is 0. And trace, that means sum of diagonal elements, is equal to 0. trace is 0. Well, so I have discussed antisymmetric matrix. Now let me discuss a little bit about eigenvalues of antisymmetric matrix. So eigenvalues of antisymmetric matrices are purely imaginary numbers. This is something that has to be remembered by you. Eigenvalue or eigenvalues of an antisymmetric matrix are purely imaginary numbers. But the condition is that the non-diagonal elements, that means this and this, the non-diagonal elements or the off-diagonal elements should be real numbers. This is one condition. Otherwise, the eigenvalues would be real numbers. Okay, so let us see about eigenvalues. So there are two things. The matrix could be even. Suppose you have been given an antisymmetric matrix, it could be even and it could be odd also. What do I mean by even? Suppose if it is 2 by 2 antisymmetric matrix or 4 by 4, then it is even antisymmetric matrix. And if you are given 3 by 3 or 5 by 5, then they are odd antisymmetric matrix. But if you are given an antisymmetric matrix and the non-diagonal elements are real number, then 2 by 2 for 2 by 2 matrix, two eigenvalues are possible, and both the eigenvalues will be imaginary numbers. Suppose one is 1 plus I, then the other will be 1 minus I. For 4 by 4, there are 4 eigenvalues possible. Suppose if one is 1 plus I, then the other will be 1 minus I. Suppose the next is 3 plus 2i, then the next will be 3 minus 2i. 4 eigenvalues and it has 2 eigenvalues. We are supposing these numbers. Exactly, we don't know because we don't have any matrix. Now suppose there is an antisymmetric matrix of odd order 3 by 3 and all the non-diagonal elements are real numbers. Then for this we could have 3 eigenvalues. 2 eigenvalues will be imaginary numbers, purely imaginary numbers like this, but the 1 will be 0. For 5 by 5, similarly, one eigenvalue will be 0 and the rest 4 eigenvalues will be purely imaginary numbers. Suppose one is 2 plus 3i, then the next will be 2 minus 3i. They are in pairs. This is also something that has to be remembered. And suppose the next is 3 plus I, then it will be 3 minus I. So we understood that if we have an square matrix, I should say if we have an antisymmetric matrix which is satisfying all these 3 conditions, it doesn't matter whether it is even or odd, but it should be antisymmetric matrix and all the non-diagonal elements are real numbers, then for even antisymmetric matrix, the eigenvalues are purely imaginary. Purely imaginary means it contains i's, and also they will be in pair. If one is 1 plus I, it will be 1 minus I. And for 4 by 4, they are also in pair, 1 minus I, and these are also in pair. But for an odd antisymmetric matrix, 2 eigenvalues are imaginary numbers, purely imaginary numbers, but 1 would be 0. And for 5 by 5, 4 eigenvalues will be imaginary numbers and they will be in pair also, but 1 will be 0. So that is something to be remembered. But now what I am telling you, that you forget everything that I have told you up to till now. Okay, you have to forget what I am saying, so because it doesn't matter whether the matrix given is symmetric or antisymmetric, or it is neither symmetric nor antisymmetric, it just doesn't matter. You have to treat it as a normal matrix, and you know what is the way to find the eigenvalues to a matrix. We know there are standard formulae, standard equations, and using any of those equations we can find the eigenvalues. So these are not the things that we have to use. Only only this is to be remembered. Since it has been told that this is antisymmetric matrix, so this is to be remembered. This is one convenience that we are provided when the matrix is antisymmetric matrix. Otherwise the eigenvalues we will finally get, we don't have to think about it, that whether that is even odd, and the one for odd antisymmetric matrix one eigenvalue is 0 and the two are uh, imaginary numbers. For 3 by 3 and for 5 by 5, 4 are imaginary and 1 is 0. We don't have to think all these things, but we have to go by the general law. So I want to do this. We already know that for finding the eigenvalues for a matrix, let us suppose that this is the matrix we have been given and we have to find the eigenvalues to this matrix. So there are two ways. One is the using characteristic equation. This is also called secular equation, and this is what a minus lambda I determinant equal to 0. But we generally don't use this because this is very lengthy process and little hectic. And the second process is characteristic polynomial equation, that is lambda cube minus s1 lambda square plus s2 lambda minus determinant of matrix equals to 0. Now we will use this process to find the eigenvalues of this matrix. When we are using any one of the standard equations, remember we are not just thinking about what kind of matrix is it symmetric, it is antisymmetric, anything like that. We are not thinking. Since it has been told that it is antisymmetric, so we know that its determinant would be 0. This is one convenience, you will understand later. Okay, so we are using this. So to find the eigenvalues, and we will use this equation, and for using this equation we need to have s1 s2 and determinant of a. Now s1 is what? S1 is the sum of diagonal elements, we know this. Now sum of diagonal elements means this is our matrix, these are diagonal elements and their sum. This is also called trace. So s1 is 0. Now s2 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 is sum of minors of diagonal elements. So this is the first diagonal element, and the minor of this element, how to find? We just erase this row, we erase this column. So what we are left with? 0 into 0 minus n1 into minus n1, 0 into 0 minus n1 into minus n1, 0 into 0 minus n1 into minus n1 plus minor of second diagonal element. So we will erase this column, we will erase this row. So what we are left with? 0 into 0 minus n2 into n2, 0 into 0 minus n2 into n2 plus minor of third diagonal element. This is the third diagonal element. So erase this column, erase this row. What we are left with? 0 into 0 minus n3 into minus n3, 0 into 0 minus n3 into minus n3. Okay, so this is minus minus plus n1 into n1 n square, n1 square, sorry, and this is minus into minus plus n2 into n2 square, and this is minus into minus plus n3 into n3. This is s2, sum of minors of diagonal elements, and determinant of a. Since it has been already told that this is antisymmetric matrix, so here we have a convenience that we know its determinant would be 0. So this is one convenience that we could have when it has been told that it is antisymmetric matrix. So this is 0. Now we will put all these ingredients in our characteristic polynomial equation to find the eigenvalues. So we have lambda cube minus s1 is 0, so s1 lambda square is 0 plus s2 lambda. Now s2 is n1 square plus n2 square plus n3 square into lambda minus determinant of a is 0 is equals to 0. So lambda cube plus n1 square plus n2 square plus n3 square into lambda is equals to 0. If we take lambda as common, we have lambda square plus n1 square plus n2 square plus, I'm sorry, we have n1 square plus n2 square plus n3 square is equals to 0. We have what we have done, we have written first of all this, then lambda cube equal to, this is just simplification, then we have taken lambda as common from both these terms. Now we cannot do one thing, that we cannot take this lambda to the right side and make it 0, because we need the value of lambda. So what we can do, this term is individually equal to 0 and we make this term individually equal to 0. So lambda is equals to 0 individually, and lambda square plus n1 square plus n2 square plus n3 square is individually 0, and this is already one eigenvalue we have found. Now from here we have to see that from here lambda square is equals to minus of n1 square plus n2 square plus n3 square. So lambda is equals to plus minus root over of minus of n1 square plus n2 square plus n3 square, obviously. So we have plus minus, we can, this is minus 1, we can take out root of minus 1 and we can have root over inside n1 square plus n2 square plus n3 square. I don't think you have any problem about this. Okay, and this is, we know that I, root over a minus I. Now ni square plus n2 square plus n3 square, and this value is 1. Why do I say so? This is because it has been told in our problem that n1, n2, n3 are components of a unit vector. Now when these are unit vectors and they are in this form, root over n1 square plus n2 square n3 square, its value is 0. Now how do I say that? This is because of the reason that suppose we have a matrix vector A, or sorry, vector that is A, it is 2 I cap plus 3 j cap plus 4 k cap. Let us suppose, then 2, 3 and 4 are the components of vector A but not the components of unit vector. But in our problem it has been said that they are unit vectors. So in this problem, we let us find unit vector of A, that is, we know that vector A by mod of vector A. Now mod of vector A, we know how to find, root over of 2 square plus 3 square plus 4 square, that means root over of 29. That means it is vector A by root over of 29, and that means 2 by root 29 I cap plus 3 by root 29 j cap plus 4 by root 29 k cap. Now this is the unit vector, and here this component and this component and this component, these three components are now components of the unit vector but not for the vector. And when these are the components of unit vector, and if they are written in the fashion under root and all the components are squared and summed, 4 by root 29 square root, then what we have, we will have, this is 4 by 29, this is 9 by 29 plus 16 by 29 is equals to root 29 by 29. This gives us root 1, that means 1. That means whenever the components of a unit matrix are written in this fashion, then it gives us 1. And this is the same thing that has been told, that in our problem it has been told that n1, n2 and n3 are components of a unit vector, and if they are written in this fashion, then its value is 1. And that is why we have only plus I minus I into I. That means plus I and minus I. So we have three eigenvalues. What are those? The three eigenvalues are We already have lambda equals to 0 here, lambda equals to 0 and plus I minus I. So 0 plus I minus I. Recall that I have already told you, if the antisymmetric matrix is odd, then one eigenvalue will be 0 and the rest of the eigenvalues will be imaginary numbers, purely imaginary numbers, and they will also be in pair, plus I, if one is plus I then one is the minus I. So this really satisfies our discussion. So this is the answer, and for this we have option A. So answer is A. Thank you.